Okay, so just doing some brief revision of the trapezium rule. So finding the area underneath the curve is quite important for mathematicians, and this has puzzled mathematicians for hundreds of years how to find an appropriate approximation for the area underneath a curve. Okay, so let's look at a practical example. Let's say we throw a stone and we get a formula that the velocity is equal to t squared. And we want to find the distance travelled between 2 and 3 seconds. So we get velocity there and t there. So the area underneath the curve between 2 and 3 is going to be the distance travelled by the stone or particle. We've got a variety of shapes we can use to split this area up. We could use a rectangle. Let's have a look at using a rectangle. Got red. We could split this up into rectangles. Okay, and this will give you an error, which I'm going to colour in. Here. But there's a better shape which we could use where the side of the shape isn't at a right angle, and that shape is a trapezium. Remember, the only condition for a trapezium is 2 parallel sides. And this side here better approximates a curve. You can see the error on a trapezium is smaller than the area of a rectangle. The error here. Let's note all of this. So let's have a look at deriving the formula which we saw on the first page. This formula here. Okay, so let's consider a familiar graph, which is y equals x squared. And let's consider 2 points, A and B, x-axis, y-axis. And let's split this up into, 4 trapeziums. 2, 3, 4. Okay, so each of these trapeziums is going to have a height h. H, 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 H. Each can have a height h. And it's going to have a side length of y0, y1, y2, yn minus 1, and yn. Okay, so there's a little bit of notation here. We're saying that y of 0 is the same as a squared. We're saying y1 is the same as a plus h squared. Y of n is the same as b squared. is equal to b. Okay, so once we get over the notation, perhaps we can start working out our formula. Okay, so we have area, we use this approximation, and we need to find the sum of the areas of each of these trapeziums. Let's label them. Let's label them trapezium 1, 2, 3, and 4. Okay, so trapezium 1 is just going to be half h y0 plus y1. Trapezium 2 is going to be half h y1 plus y2. Trapezium 3 is going to be half h y2 plus yn minus 1. And trapezium 4 is going to be half h yn minus 1 plus y of n. Now, I'm sure we can simplify this untidy formula. Okay, so we can take out half h, because we've got half h throughout the formula. I'm just going to count how many y of zeros we have. We've got one y of 0, and that's it. Let's count how many y of n's we've got. Just got 1. So we can put this at the beginning of the formula. y0 plus y of n. Okay, so just be aware that different mathematicians choose to write the trapezium formula differently. So you should be aware that this formula can be written differently depending on the mathematician. But the concept is the same. We are just summing the number of trapeziums over the interval. So let's carry on counting our variables. We've got 1, 2 y of 1s, we've got 1, 2 y of 2s, and we've got 1, 2 of yn minus 1, which is just the height of the trapezium before the final interval. Okay, so we can take a 2 out there, y2 plus yn minus 1, close brackets. Now the final thing we need to do is we need to define this h value, which is the height of the trapezium. So I'm going to do this using, let's do it using purple. Okay, so we've got a height there, and we've divided this interval up, b minus a, into n partitions. So we know that one individual height is going to be the distance b minus a divided by n. Okay, so let's look at a practical example. Just going to put a box around this. Now would be a good time to pause the video and see if you can derive this formula yourself. You need to draw any function, any graph, which is non-linear, divide it up into partitions of between a and b, and draw in your trapeziums. Okay, so let's look at a practical example. Let's find the area underneath the curve of y equals x squared. Let's call this x and y, and that's 2 and 3, and let's do just 1, 2. two trapeziums. So the first thing we need to find is the height of the trapeziums. Well, using our formula, b minus a all over n, we've got 3 minus 2 divided by 2. So the height of each trapezium is going to be half, with whichever units we are using. So here we've got 2.5. So again, just using our notation, we've got y of 0, which is the first term. We've got y1, which is just the term before y of n. So let's relabel this n minus 1. Then we've got y of n. Okay, so let's write our formula out first. So our formula was half h y of 0 plus y of n plus 2 y1 plus y2 plus 2 plus y of n minus 1, close brackets. Okay, now this time we haven't got very many trapeziums. So this is a nice easy one. So we've got half of the height plus y of 0, which is just simply 2 squared, plus yn, which is the last, which is the length of the final trapezium 2, which is just going to be 3 squared, plus 2 of the middle height, yn minus 1, which is just simply 2.5 squared, and we don't have any other lengths to consider. Okay, so on your calculators, if you work that out, you're going to get 6.375 units squared to 3 decimal places. Okay, so I want you to pause the video now and consider what would happen to our result if we partitioned the area underneath the curve into more trapeziums. Okay, so hopefully you've paused the video and considered what would happen to the area underneath the curve if we partitioned more than 2 trapeziums. So let's rub this out and let's find the area using more than 2 partitions. Okay, so this time let's just use 3. So we've got y equals x squared. We've got our x-axis, got our y-axis. We're just using 2, 3. Okay, now if you remember, our formula for the height was b minus a all over n. 3 minus 2, this time n is 3 because we are partitioning 1, 2, 3. So our height is going to be 1/3. So we've got 2 1/3, 2 2/3, and then finally 3. So we've got y0, y of 1, y of n minus 1, y of n. Now, the biggest confusion I find with students is this notation, y0, y of 1, y of n minus 1, and y of n. Now, to get rid of any confusion, I'm just going to write what these actually mean. Y to 0 is simply the first length of our trapezium, which is just going to be 2 squared. Y of 1 is just going to be simply 2 1/3 all squared. Yn minus 1 is just going to be simply 2 2/3 squared, and then y of n is going to be 3 squared. Now, where do we get these from? Where do we get these from? And how do we find them? Okay, so I want us to look at the equation of this line. The equation of this line is y equals x squared. If we are finding the x value, if we are finding the y value, when x is equal to 2, 2 1/3, 2 2/3, and 3, we just simply put each of these values into this formula. And that's where we get these from here. It's really important that you understand that. Okay, so let's work out the area. And I always start by writing the formula first before we substitute in. So we got half h, square brackets, y0 plus y of n plus 2 of y1 plus y2 yn minus 1. Okay, so we got our formula. This time the height is 1/3, and we've got y of 0, which is 4, y of n, which is 9. By the way, this is going to be the same no matter how many partitions you have, because the length of the first height and the length of the last height is going to stay the same. It's going to stay the same. Plus we've got 2. Y of 1 is simply 2 1/3 all squared. And then we've just got y of n minus 1 is 2 2/3 squared. And we need to make sure we got the same number of left-hand parentheses and right-hand parentheses. I've just used square brackets to distinguish between the total sum here and the smaller sums. Okay, so let's put this in our calculator, and we're going to get 6.351 units squared to 3 decimal places. Okay, so the result is changing slightly, and at the end we'll look at the results more closely. Okay, so let's partition now using 6 intervals, using 6 trapeziums. So let's do that then. Let's rub this out and redraw the graph using 6 trapeziums. And I want you to make sure that you're noting down the area we got for 2 partitions, 3 partitions, and the one we do now, which is 6 partitions. Okay, so let's draw our graph. Let's get rid of that. Block that. Okay, so two, 1, 2, 3, 4, 5, 6. Okay, so let's label this then. 1, 2, 3, 4, 5, 6. So let's use our formula to find the height. Remember, the height was b minus a divided by n, or 3 minus 2 divided by 6. That just gives us 6. Okay, so this is going to get messy because we have to fit each of these onto the graph here. So let's just write 2 and 6, 2 and 2 sixths, 2 and 3 sixths, 2 and 4 sixths, and 2 and 5 sixths. Okay, I'm not going to write each of these because that would be too fiddly, but I will define y of n minus 1, and this is y of n. I will define the first one, y of 0, which is just simply 2 squared, y of 1, which is just going to be 2 and 1 over 6 squared, y of 2 is simply going to be 2 and 2 sixths squared, and the last one, y of n, is just simply going to be 3 squared. So please make sure you know where each of these came from. Okay, I'm going to rub these out, and then I'm going to write down our lovely formula for the approximation of the area of a trapezium. So we got A is an approximation, half h, square brackets, y0 plus y of n, 2 y1, y2, y of n minus 1. Okay, so let's start substituting in values. We got half, the height, which is sixths, and that is been rubbed off there for some reason. 6. Okay, so we got 1 over 6. We got y of 0, which is just simply 2 squared, y of n, which is just simply 3 squared, plus 2. Okay, now this is where it gets a little bit fiddly. Put each of these in, squared, 2 and 2 sixths squared, plus 2 and 3 sixths squared, plus 2 and 4 sixths squared, and 2 and 5 sixths squared, close bracket, square bracket. Okay, so if you're wondering where 2 and 6 sixths it is, well, 2 and 6 sixths is just simply going to be 3, which is here. Okay, so on your calculator, being really careful that you have an equal number of right down parentheses and left down parentheses. Parentheses is just a posh word for bracket. We find that the area is 6.337 units squared to 3 decimal places. Okay, marvellous. So let's have a closer look now at the various partitions and how accurate they are, which leads us to answer our initial question is, what happens when we increase the number of partitions to the accuracy of our answer? Okay, so effectively, what was our initial question? And let's choose a nice different colour. Let's work in, don't know, my favourite colour, turquoise. Okay, so our original question was to find an estimate of the area underneath the curve between 2 and 3, x and y, of the graph y is equal to x squared. Now, we can use other methods in mathematics, using calculus, to find the exact area. And if you're interested in the notation, we can use this notation. That means area is called an integral between 2 and 3 of x squared dx. And this notation might not mean anything to you until you've studied calculus. And we can find out that the exact area is 6.334 units squared to 3 decimal places. Okay, now that's the exact value. Don't worry too much about this notation if you haven't studied it. Okay, so let's have a closer look now at our n values. Okay, so let's do n, let's do our value, and let's consider percentage error. Now, our first n value was 2, and we got an area of 6.375, and miraculously that gave a percentage error of 0.65% to 2 decimal places. Now, what do you think is going to happen as we increase the number of partitions, and hence the number of trapeziums, and more importantly, why? Why does this happen? Well, let's have a look. If we increase to 3, we get 6.351, and we get an error of 0.27%. And then, if we have 6 partitions, we get 6.337, a very small error of 0.05%. So what conclusion do you draw? Well, hopefully you can see that as you increase the number of trapeziums, in other words the partition, the more accurate the result becomes, because look, 2 partitions gives an error of 0.65%, 3 partitions gives an error of 0.27%, and 6 partitions gives an error of 0.05. And hopefully you're able to see, just through drawing trapeziums, that by increasing the partition, we decrease the error area and hence make the result more accurate. Okay, marvellous, and I hope you enjoy doing some more numerical integrations using the trapezium rule.